100 years ago, we finally discovered the secret of the universe, the Big Bang. Until then, it was believed that the universe was eternal and perfect, and such a perfect universe was thought to be God itself. However, as science developed, we realized that there is no God who orchestrates everything in the world. Nevertheless, if God exists, it was thought that this God would be a transcendent being who created the universe. Perhaps because of this, scientists have been desperately trying to uncover the secrets of the universe that gave birth to us humans. And finally, they reached the point of discovering that the beginning was the Big Bang. So, what exactly happened after the Big Bang? How did the universe begin? Today, let's explore from our cozy corner. How did the universe begin? Let's start right now. Feel free to ask if you need any further assistance. The most powerful explosion in the history of the universe that started from a single point, the Big Bang. However, this explosion was not like the explosion of a bomb, as we might think. The explosion referred to in the Big Bang was not strictly speaking an explosion, but merely the phenomenon of the universe expanding in size. Therefore, the expression that the Big Bang happened at a single point is actually incorrect. Before the Big Bang, there was neither time, space, nor dimensions that could be called a point. Thus, the question of what existed before the Big Bang is flawed from the premise. But for convenience, let's start by assuming the Big Bang was an explosion that occurred at a single point. Right after the Big Bang, space began to emerge suddenly, and all particles began to move away from each other to fill the newly created space. At this moment, the temperature of the universe, which had just exploded and held immense energy, was a staggering 1.5 trillion Kelvin. This temperature was unimaginably high, roughly 100,000 times the core temperature of the Sun, which is about 15 million degrees. At such an extremely high temperature, all particles would start to move wildly due to the overwhelming energy, making it impossible for current science to explain what happened at that time. Considering that the target temperature for our current nuclear fusion projects is 100 million degrees, we can grasp how extraordinarily high 1.5 trillion K is. However, if this temperature dropped to around 100 billion K, it would be possible to predict what might have been happening in the universe at that time. So, how long did it take for the universe at 1.5 trillion K to cool down to about 100 billion K? Surprisingly, it took only 0.01 seconds. At that time, the entire universe was only about 4 light-years in size, and even after filling all of it with energy, the remaining temperature was 100 billion K. In this era, the universe was in an ultra-high temperature state where even atomic nuclei could not survive, and only positrons, electrons, neutrinos, photons, and radiation energy existed. Among these, electrons were the ones we know, the negatively charged particles surrounding atomic nuclei. And in the early universe, there were countless numbers of them. There were also many positrons, which were particles identical to electrons in every way, except that they had a +1 charge. Today, positrons are very rare and can only be observed in laboratory nuclear reactions or supernova explosions in space. But back then, they were so abundant that they were spread throughout the entire universe along with electrons. The next material that filled the universe was neutrinos, which were mysterious particles that only interacted via the weak force and gravity and did not interact with other materials. Not interacting means, simply put, that no matter what material was in front of these neutrinos, they would pass through as if nothing was there. Lastly, there was a vast amount of light, or photons, which, unlike the previous 3 materials, had no charge or mass but only carried energy. These particles collided countless times at unimaginably high temperatures, repeatedly undergoing processes of creation and annihilation, and eventually reached a state of thermal equilibrium where the amount of heat exchanged was equal. During this period, the fundamental particles of matter, quarks and gluons, finally appeared. Quarks are the most basic particles of all matter. If the phone or computer you are watching this video on is made up of various metals, those metals are made up of countless atoms. And those atoms consist of protons and neutrons, which in turn are made up of quarks. And gluons are, simply put, the adhesive that binds protons and neutrons, the assemblages of quarks. This indicated that something material was beginning to form in the universe. However, unfortunately, the basic particles of matter, protons and neutrons, were very scarce in the universe at that time. Roughly speaking, if there were 10 billion photons, neutrinos, electrons, and positrons in the universe, there was only about 1 proton and neutron. But as time passed, that ratio slowly began to rise. Thus, 0.11 seconds after the Big Bang, the temperature of the universe, which had been 100 billion K, dropped to 30 billion K. Most of the universe was still occupied by electrons, positrons, photons, and neutrinos, and the number of protons and neutrons was still sparse. However, during this period, the universe underwent a period of dramatic change. As the temperature dropped to 30 billion K, a phenomenon occurred where neutrons and protons converted back and forth into each other. Heavier neutrons turned into lighter protons, and vice versa. This process repeated, and as the temperature of the universe gradually decreased, the relatively heavier neutrons became less active and converted more into the lighter, more active protons. At this time, the ratio of protons to neutrons was 62% to 38%, respectively, and over a long period. This started to form the foundation of the universe. Then, 1 second after the Big Bang, the temperature of the universe dropped from 1.5 trillion K to 10 billion K in just 1 second. As the universe expanded and the temperature dropped, the activity of matter decreased, and changes gradually diminished. However, protons and neutrons continued to switch roles, and at that time, the ratio of protons to neutrons was 76% to 24%. 14 seconds after the Big Bang, the temperature of the universe reached a relatively low 3 billion K, and the early structure of the universe began to take shape. Usually, applying high pressure to a gas can turn it into a liquid, like liquid nitrogen, which we can see around us. However, no matter how high the pressure, if the temperature is too high, the gas cannot turn into a liquid. This threshold temperature is called the critical temperature. If the temperature is above this critical temperature, no matter how much it is compressed, there is no change in the state of the material. Only when the temperature is below this critical temperature can the state change occur. Each material has a different critical temperature, and this period was when the universe reached the critical temperature for electrons. As the temperature of the universe reached the critical temperature for electrons, electrons began to annihilate rapidly. During the annihilation process, energy was released according to E equals mc cc2, temporarily slowing down the cooling rate of the universe. As time passed and the temperature of the universe decreased, the universe began to build up to its current state. It was the perfect time for helium to be formed. Though one might think that the high temperature and pressure of the universe would make helium formation easy, the universe was expanding at an unimaginable rate, making it impossible for particles to meet and undergo nuclear fusion. Instead, protons and neutrons wandering the universe collided quickly and formed helium by chance. In simple terms, when 2 protons and 1 neutron collided, helium-3, He3, was formed. And when 1 proton and 2 neutrons collided, tritium, H3, was formed. When another neutron collided with helium-3, the first helium nucleus we know, with 2 protons and 2 neutrons, was finally formed. This process lasted about 3 minutes, and 3 minutes and 46 seconds after the Big Bang, the universe reached a relatively cool 900 million K. 900 million K was a good condition for nucleosynthesis to occur. Numerous protons and neutrons in the universe began to undergo nucleosynthesis in earnest, creating hydrogen and helium, thus laying the foundation of the universe. The ratio of hydrogen to helium created at this time was about 3:1, and surprisingly, the current ratio of hydrogen to helium in the universe is also 3:1. This, along with the cosmic microwave background radiation, is strong evidence that this universe was born from the Big Bang. After countless nucleosynthesis, the universe began to fill with hydrogen and helium, a process that lasted for tens of thousands of years, eventually reaching a temperature of about 2.725 K. Thus, the long and arduous journey of the Big Bang finally came to an end. Now, the hydrogen and helium born from the Big Bang began to fill this vast universe. The hydrogen and helium, evenly distributed throughout the universe, were drawn together by their own mass due to gravity, forming higher-numbered elements, rock masses, stars, galaxies, and so on. Countless stars were born and died, and about 9.2 billion years later, our Sun and Earth appeared in this universe. Even after that, the universe continued to actively form stars, and about 4.6 billion years later, humans appeared on Earth, striving to unravel the secrets of this universe. However, there were some strange aspects to the Big Bang, which holds all the secrets of the universe. In 1915, the story of the universe was born based on Einstein's general theory of relativity, the Big Bang theory. However, like all the theories that changed the paradigm of their time, the Big Bang theory faced fierce opposition from all directions from the moment it was announced, taking decades to be accepted as the established theory in academia. This wasn't simply because scientists were being stubborn or lacked knowledge, but because there were many strange aspects to the Big Bang theory. After the announcement of the general theory of relativity in 1915, which changed the paradigm of modern science, Einstein was constantly thinking about the universe every day. When researching his masterpiece, The General Theory of Relativity, he found that the story of the universe was very different, or rather, strange, from what he had imagined. According to the General Theory of Relativity, all objects with mass should each have their own gravity. This is an obvious fact. However, the problem was that the numerous celestial bodies in this universe all had astronomical masses, which means they all had enormous gravity. Gravity is an immense force that cannot be ignored, and no matter how far apart objects are, gravity can never be zero in this universe. Although the force of gravity is inversely proportional to the square of the distance, it can never be zero because there is no negative gravity. Therefore, all celestial bodies should be drawn to each other's gravity, causing the universe to contract, since there was no way Einstein's general theory of relativity could be wrong. So, if the universe was indeed contracting due to the immense gravity as suggested by the general theory of relativity, it should have rapidly contracted to reach the state of the Big Bang. However, the universe did not show signs of contraction. Instead, it appeared to be in a calm state. Therefore, in 1917, 2 years later, Einstein proposed a static universe, ignoring the fact that the universe could change according to the general theory of relativity. But as you know, in 1927, the Belgian astronomer Georges Lemaitre discovered that the universe was expanding based on Einstein's equations. This raises a question. According to Einstein's general theory of relativity, each celestial body must have immense gravity. Yet, for some unknown reason, the universe is expanding. Let's assume that this expanding force is strong enough to overcome gravity. Even with this assumption, there were still problems with the Big Bang. If the expanding force was strong enough to ignore interstellar gravity, it could prevent the universe from contracting. But this would also mean that celestial bodies could never get close to each other. In that case, could celestial bodies exist in this universe? According to hundreds of years of scientific research, all celestial bodies in the universe are formed by space dust and gas clumping together under their own gravity. If the expanding force significantly exceeded gravity, these materials would disperse before forming celestial bodies. The Earth we live on, the sun that shines on us, and all celestial bodies in the universe would never have been born. This means that if the expansion speed was too slow, the universe would rapidly return to the state of the Big Bang due to the gravity of all celestial bodies. Conversely, if the expansion speed was too fast, materials would scatter without forming celestial bodies. In summary, for the universe, which has a history of 13.8 billion years, to maintain its current state, it had to have exactly the right expansion speed. This wasn't the only thing that needed to be just right. The Big Bang theory, initiated by Einstein, Lemaitre, and Hubble, was completed by NASA's WMAP probe launched in 2003. WMAP provided strong evidence for the Big Bang by capturing the state of the universe 380 years after the Big Bang, showing that the universe was evenly distributed right after the Big Bang. This discovery revealed that the universe was surprisingly uniform. However, this finding also raised more questions about the Big Bang. How could the universe be so uniform? If there had been even a slight unevenness, areas with dense celestial bodies would have had immense gravity according to the general theory of relativity. These areas would have eventually developed into black holes if they exceeded the limit mass and gravity, leading to a universe filled with black holes. However, celestial bodies were designed to have only indirect effects on each other, avoiding a universe dominated by large black holes. Looking up at the sky, the seemingly chaotic universe is actually very uniform. How did this happen? Was it divine intervention that designed this uniform universe? Fortunately, this question about the Big Bang could be explained by one theory. That famous theory is the inflation theory. In the early stages of the Big Bang theory, it was thought that the universe expanded gradually to its current state. However, it turned out that the universe underwent tremendous rapid expansion at the 10-10-10-43 second mark after the Big Bang. The size increased by a factor of 1030. If the universe had expanded slowly at a similar speed, celestial bodies couldn't have been distributed this uniformly. But because the universe expanded by a factor of 1030 in an unperceivably short 10-10^43 second, it had no choice but to become uniformly distributed. Due to this instantaneous expansion, we have a relatively uniform universe, and the residual energy is the cosmic background radiation measured at 2.725 K across the universe. However, this fact brought another question. If the universe underwent rapid inflation and became highly uniform, the early universe must have maintained an adequate distance from each other. However, the problem was that if all the matter in the universe maintained such a perfect balance, celestial bodies like our Earth could never have been formed. Particles in the universe need to collide, break apart, and gather together to form celestial bodies like ours. If the attractive forces were in perfect harmony and the state was too uniform, they wouldn't affect each other, and no celestial bodies could form in this universe. Therefore, the universe had to be uniform, but at the same time, it needed a certain degree of non-uniformity. In 1965, Penzias and Wilson discovered the evenly spread cosmic background radiation as evidence of the Big Bang. But now, the problem was that if the universe was too uniform, celestial bodies like our Earth couldn't form, leading to a troubling situation. In this ironic situation, NASA launched the Cosmic Background Explorer, COBE, in 1992 to observe the cosmic background radiation more precisely. As a result, it was confirmed that the universe, which was thought to be perfectly uniform, actually had some slight irregularities. Later, in 2012, the Wilkinson Microwave Anisotropy Probe was launched for more precise observation, confirming that there were more slight irregularities than previously thought. Finally, in 2013, the European Space Agency launched the Planck satellite, revealing that the universe is incredibly uniform, yet at the same time, non-uniformity is evenly spread. An ironic situation. Thanks to this harmony of uniformity and non-uniformity, we were able to escape the fate of a universe full of black holes. At the same time, stars like the Sun, planets like Earth, and life forms like humans could be born. In summary, the universe is well explained by the Big Bang, with the right expansion speed that allowed matter to clump together appropriately without collapsing, the rapid inflation of 1030 times in 1043 seconds, and the right non-uniformity for life forms like us to be born. It seems we have somewhat unraveled the secret of the birth of our universe. But if there is a beginning, there must also be an end. How will our universe end? The next science topic we will explore is, how will our universe end? This has been Science from the Living Room.